In this lesson, we'll explore one of the most important concepts in Kafka Connect offset storage. Offsets are what allow Kafka Connect to remember its progress as it moves data between systems. Without offsets, a connector would have no idea where it stopped previously. Every restart would either begin from the beginning, causing duplicate processing, or potentially skip data altogether. Neither of those situations is acceptable in a reliable data pipeline. Throughout this lesson, we'll look at how Kafka Connect stores offsets in standalone mode and distributed mode, why the storage mechanism matters, and how it affects reliability, scalability, and fault tolerance. If you already completed Kafka fundamentals, you will notice some similarity to consumer offsets. However, Connect uses offsets slightly differently because it needs to track progress for connectors rather than just consumers. Let's start by looking at this diagram. The upper half of the diagram represents a source connector. On the left, we have a source system, which could be a database, a file, or another external system. The source connector continuously reads data from that system. As it reads records, it also remembers how far it has progressed. That progress information is called an offset. Notice, the connector doesn't only write records into the Kafka topics, it also writes its current offset into offset storage. This allows the connector to remember exactly where it stopped. For example, if the connector is reading from a database, the offset might be the last transaction ID, row ID, or timestamp that has already been processed. If it's reading from a file, the offset could simply be the byte position or line number within that file. Now let's look at the bottom half of the diagram. Here we have a sink connector. Instead of reading from an external system, the sink connector reads data from a Kafka topic and writes it into a target system, such as a database, Elasticsearch, or Amazon S3. For sink connectors, the offset represents the Kafka position that has already been processed. Typically, this consists of the topic name, partition number, and the last consumed offset within that partition. Just like the source connector, the sink connector periodically stores its progress in offset storage. Why it is important? Imagine the connector crashes halfway through processing millions of records. When it starts again, it doesn't need to begin from scratch. Instead, it simply reads its previously stored offset and resumes from exactly where it left off. This ability to resume processing makes Kafka Connect highly reliable and minimizes duplicate processing. Now let's see how offset storage works in standalone mode. In this diagram, we have a single Connect worker running in standalone mode. That worker may be running multiple tasks, but all of those tasks write their offset into the same local file on the machine. You can see both task 1 and task 2 writing their progress into a single file specified by the offset.storage.file.filename property. Inside that file, Connect stores offset information in JSON format. Each connector task has its own entry that records its current position. This design is very straightforward. Everything stays on one machine, making it easy to understand and debug during development. Let's look at the configuration shown on the slide. The first property, offset storage file name, specifies where Kafka Connect should store its offset file. In this example, the offset will be written to valid Kafka Connect offsets. You should make sure this directory exists and that the Connect worker has permission to write to it. Offset plus interval millisecond. This controls how frequently Connect writes its in-memory offset to disk. In this example, offsets are flushed every 10 seconds. Choosing this value involves a trade-off. If you flush very frequently, such as every second, you minimize the amount of progress that could be lost during a crash. However, you will perform more disk I/O, which may slightly reduce performance. If you flush less frequently, you reduce this activity, but risk replaying a larger amount of data after a failure because recent offsets may still exist only in memory. Now let's move to distributed mode, which is the deployment model used for most production environments. Instead of storing offsets in a local file, every Connect worker writes offsets into an internal Kafka topic. In this diagram, we have multiple connect workers running simultaneously. Worker 1 owns task 1 and task 2, while worker 2 owns task 3. Although these tasks run on different machines, they all write their offsets into the same shared internal topic named connect-offset. This topic lives inside the Kafka cluster itself. Since Kafka replicates topics across brokers, the offset information becomes highly durable and fault tolerant. Notice the worker restart shown on the diagram. Suppose worker 1 suddenly crashes. Kafka Connect automatically redistributes its task to another worker. When the new worker starts executing those tasks, it first reads the latest offsets from the connect-offset topic. Because every worker shares the same offset storage, processing continues from exactly the previous position without needing any manual intervention. Let's compare the two deployment modes side by side. The biggest difference is where offsets are stored. Standalone mode stores them in a local file, while distributed mode stores them inside Kafka itself. Because standalone mode relies on local storage, it does not provide high availability. If the machine fails, the offsets may be lost. Distributed mode benefits from Kafka replication, making the offset data durable even if individual brokers or workers fail. Scaling is another major difference. Standalone mode is limited to a single worker, making it suitable for only smaller deployments. Distributed mode supports many workers running together, allowing connectors and tasks to be distributed across the cluster for higher throughput. Finally, consider the intended use cases. Standalone mode is ideal for development, testing, and learning. Distributed mode is designed for production environments where reliability, scalability, and fault tolerance are essential. One interesting aspect of the connect-offset topic is it uses log compaction. Unlike normal Kafka topics that retain every message until the retention period expires, a compacted topic keeps only the most recent value for each unique key. In the offset topic, the key identifies a specific connector, task, or source partition. The value contains that task's latest offset. As a connector continues processing data, it keeps writing newer offset values with the same key. During log compaction, Kafka removes the older versions while preserving the latest one. This provides two important benefits. First, the topic size remains under control instead of growing forever. Second, Connect always has quick access to the latest offset for every connected task during recovery. This makes compacted topics an excellent fit for metadata such as offsets where only the latest state is important. Let's summarize what we have learned in this lesson. Offsets are how Kafka Connect remembers its progress and allow connector to resume processing after restarts or failures. In standalone mode, offsets are stored in a local file. This approach is simple and works well for development, but lacks high availability and fault tolerance. In distributed mode, offsets are stored in a replicated Kafka topic, providing durability, automatic failover, and horizontal scalability. The connect-offset topic uses log compaction so that only the latest offset for each connector task is retained, keeping the topic efficient while preserving the most recent state. In the next lesson, we'll move on to converters and explore how Kafka Connect serializes and deserializes data using JSON, Avro, and protocol.